This was the trickiest question on the mechanics paper for A-level maths in 2023. A question like this tends to come up every year. Do you think that you're ready for it? Let's have a look and find out. It says, a rod, AB, has mass m and length 2a. The rod has its end A on rough horizontal ground, and its end B against a smooth vertical wall. The rod makes an angle of theta with the ground, as shown in the figure, and the rod is at rest in limiting equilibrium. Part A. State the direction, left or right, on the figure, of the frictional force acting on the rod at A. Give a reason for your answer. It's not enough just to say left or right, we need to explain our thinking here. Let's think of the forces acting on the rod here. So I'm not going to consider the forces acting on the wall or the ground, just the forces acting on the rod. Well, the rod has a mass m, so therefore it's going to have a weight. That's going to act vertically downwards towards the centre of the earth. What about the force at B? Well, B is a smooth wall. That word smooth indicates that there's no friction at B. The only force would be the normal reaction. Remember, the normal reaction is normal to the surface that the object is lying on. So it's at 90 degrees to the wall. Not, be careful, not at 90 degrees like this to the rod, be careful. What about the forces at A? Well, it's resting on a rough ground. So we're going to have a normal reaction. That's going to be normal again to the surface that it's lying on. Normal to the ground. Be careful, not normal to the rod like this, no. But there's going to be another force at A. That's the frictional force. How do we know there's friction there? Because of the word rough in the question. It's a rough horizontal ground. So which way will friction act? To the left or to the right? Well, there's different ways of thinking about this. Perhaps the easiest way is to consider that we know that the rod is at rest in limiting equilibrium. That must mean that the forces are balanced, both vertically and, crucially, horizontally. So there must be a force acting towards the right to balance out the normal reaction at B. Otherwise, the forces horizontally would be unbalanced, and the rod would be accelerating towards the left, and that's not happening. So to score the mark, you could say the normal reaction at B is acting towards the left, so friction must act towards the right. Or you could say friction acts towards the right, it needs to balance, or oppose, counter the force at B. Or you could say friction acts towards the right to prevent the rod from sliding or slipping or falling, however you want to word that. Think about what would happen if the rod started to slip. It would want to slip this way. So friction always acts to oppose any motion. Friction would act towards the right to counter the movement towards the left. Another way to consider this is to think about the weight force. It will have a component acting perpendicular to the rod, but also a component acting parallel to the rod. So that's pushing the rod into the ground this way, and therefore pushing it towards the left and also downwards. But we know that the rod isn't moving, so there must be, in particular, a frictional force to oppose this component of the weight acting parallel to the rod. So you could say something like, the mass or the weight will be pushing the rod to the left, so friction will want to oppose that motion. Next it says the magnitude of the normal reaction of the wall on the rod at B is S. So you can see that labelled here on the diagram. It says in an initial model, the rod is being modelled as a uniform. What does that mean? Well, it means that the mass, the weight of the rod, acts at the midpoint of the rod, perfectly at the centre of the rod. Remember, the length of the rod was 2a. Therefore, the weight will act at the midpoint, half of 2a, that's length A from capital A, and the same length from capital B. I've labelled the weight mg because the mass is m, and we know weight equals mass times this gravitational constant here, 9.8. G for short. I've labelled the normal reaction at AR and the frictional force F. Those are all of the forces acting on the rod. Make sure you don't miss any out. There are also other forces acting, of course, but they're on other objects. There's a force acting on the wall, there's a force acting on the ground, but we're not considering those. We're considering the forces on the rod here. So it says in part B, by taking moments about A, show where this formula comes from. Show that this is true for 3 marks. So we must follow that instruction. We must take moments about A. So this is where we're taking moments about. Notice that mg would be taking us clockwise around A, whereas S would be taking us anti-clockwise about A. Let's start with the anti-clockwise force. So that's S here. Notice that S is acting in this direction. That's the line of action of this force, that line there. So I can multiply the force, multiplied by the perpendicular distance from the pivot point, from A, to that line of action of the force. Where is that perpendicular distance? Well, it's here. Notice that this highlighted in pink would be perpendicular to the line of action of that force. How do I find that pink length? Well, notice that it's the same as this length here on the diagram. How can I find that? Well, if I look at this large right-angled triangle here, you can see that it's the opposite in that triangle. I know the hypotenuse is 2a. Opposite and hypotenuse, we're going to use sine. If you apply sine theta and rearrange the formula, you get, for that length there, that it's 2a sine theta. Next, we'll deal with the clockwise moments. There's only one of those due to this weight, mg. So we've got the force, Notice the line of action of this force goes this way. Our pivot is here. Where would the perpendicular from that point A to that line be? Well, it would be here. We'd have a 90-degree angle in here between the two. What is that length in pink? Well, we can look at this right angle triangle here, the smaller one. Notice that the pink distance here is the adjacent in that triangle, and we've got the hypotenuse being the length A. Adjacent hypotenuse, you should be thinking cosine. If you take cosine and rearrange it, you'll work out that that adjacent length in pink is A cos theta. If you get that far, you get your first 2 marks. Next, remember what we're trying to do? We're trying to show that S equals. So we want to get rid of this 2A sine theta. We'll do that by dividing both sides by 2A sine theta. Notice that the A would cancel. Notice here we've got cosine over sine. That's 1 over tan, which is cot. Next it says that the coefficient of friction between the rod and the ground is mu. We're told that tan of theta is 3/4. And we're asked to find the value of mu, the coefficient of friction. So remember that we are at rest in limiting equilibrium. So that means 3 things. It means that if we take moments about any point, the resultant moment, the difference between the clockwise and the anti-clockwise moments, would be 0. So the clockwise moments would equal the anti-clockwise moments. 2, it also means that if we resolve forces vertically, the sum of the upwards forces will equal the sum of the downwards forces. And 3, it means that if we resolve forces horizontally, the sum of the leftward forces will equal the sum of the rightward forces. We've already taken moments in the previous part of the question, so all we need to do is those 2 things: resolve forces vertically, resolve forces horizontally. Let's start by resolving forces vertically. You can write that as a sentence, or you can write resolve forces vertically like this for short. So, going up, we have the force R, going down, we have the weight, mg. That gets you your first mark. I've called that equation number 1. Next, we resolve forces horizontally. Going towards the right, we have F. Going towards the left, we have S. So F equals S. And remember, in part B, we showed that S was 1/2 mg cot theta. So I'm going to substitute that for S straight away. That gives me equation number 2. Finally, because we're in limiting equilibrium, we know that this frictional force will be at its maximum value. And there's a formula that you should know for that. It's mu times the normal reaction at that point. In this case, mu times R. We know that F is 1/2 mg cot theta. So we can substitute that in here by equation 2. And by equation 1, we know that R is mg. So we can substitute that in as well. Notice that the m and the g will cancel on both sides of the equation, leaving us with 1/2 cot theta. But cot is 1 over tan, and 1 over tan would be 1 over 3/4, which is 4 over 3. So we've got 1/2 multiplied by 4 over 3, that will give us 2/3. Or you can write 0.67. At least 2 significant figures there. Part D. Find in terms of m and g, so our answer is going to involve the m and the g, the magnitude of the resultant force acting on the rod at A. So let's think about the forces acting on the rod at A. We've got the normal reaction R and the frictional force F. Be careful not to confuse the normal reaction R with what they're talking about in the question. That's the resultant force. The resultant force is actually a combination of these 2 forces. It's the resultant of the 2. So we're going to need to work out what R is and what F is in terms of m and g. Earlier we worked out that R was mg, and we worked out that F was 1/2 mg cot theta. Now if tan theta is 3/4, remember cot theta, 1 over tan, would be 4 over 3. So therefore F is 2/3 of mg. So what do we mean by this resultant force? Well, it's the combination of these 2 forces acting at A. It's going to be the hypotenuse of the triangle of forces if we put F and R together acting top to tail. Think of these forces like vectors. Essentially that's what they are. Adding the 2 vectors, we're trying to find the magnitude, the resultant of that hypotenuse, the combination of the 2. So it's a right angle triangle that we've got here. We can use Pythagoras' theorem to work out the length of that resultant, the magnitude of the resultant. That would be the square root of f squared plus r squared. Now we can substitute in f, which was 2/3 mg, and r, which was mg, for our second mark. We need to square everything in this bracket. The 2, the 3, and the mg. Squaring the 2 gives us 4, squaring the 3 gives us 9, and I'm going to leave this as mg squared. Why have I done that? Well, here we've got 4/9 of mg squared plus 1 mg. 4/9 plus 1, that's 13/9 of mg squared. This square root applies to everything here. It applies to the 13, the 9, and the mg squared. So I can split that square root up into the square root of 13, the square root of mg squared, and the square root of 9. Why would I do that? Well, the square root and the square being opposites here cancel out, leaving us with mg, and the square root of 9 simplifies to 3. So we've got a nice neat final answer, 1/3 of mg root 13 for the final mark. The final part of the question says, in a new model, the rod is modelled as being non-uniform, with its centre of mass closer to B than it is to A. It says a new value for S is calculated using this new model, but with the same value as tan theta as before, so the angle hasn't changed. State whether this new value for s is larger, smaller, or equal to the value that s would take using the initial model. Give a reason for your answer. So, now the rod is non-uniform, the weight is acting at a distance, I've called it x, which is greater than the midpoint of the rod, which was a. So this is now beyond the halfway point. Remember, the rod was of length 2a. The halfway point, the midpoint, would be a. Remember, in part B, to work out s, we took moments about a, and that gave us this equation, which we then rearranged to this form. Let's do something similar now, but in our scenario, where mg is now acting at a distance, say, of x from a, where x is bigger than a. So, thinking about moments, we'll have s nu multiplied by 2a sine theta. That hasn't changed. And the only thing that would change here would be that it's mg multiplied by x cos theta, not by, as it was before, a cos theta. So when I rearrange this to make s nu the subject, the only thing that changes is that we now have an x on the top of the fraction rather than an a. So has s nu got bigger, smaller, or has it stayed the same? Well, x is bigger than a, so it must be that the new value of s is bigger than the old value of s. So, do we need to write down any of those calculations? No. What scores the marks is the following. You need to say something like, the new value of s would be larger as the moment of the weight about a, going to take in moments about a, would be larger. Why is it the weight? Well, this is the moment due to the weight, right? And that term has got bigger because x is now bigger than it was before. It was a before. That felt quite fiddly. I wonder if you've got an easier way of thinking about part E. Let me know in the comments and let me know how you're feeling about mechanics this summer.